Hello guys, Cyprien here. Today let's talk about how to simulate a 2D wave propagation. And I'm talking about sound wave and acoustics here. So that's a topic I didn't talk about so much up to now. And for this simulation I'll use OnScale. So here's the website of OnScale. So if you want to try the software, well, you can go on the website and create a free account, and you can download the software and install it on your computer for free. And then to run the simulation, then you can use the cloud. So it can run your model in the cloud, so you have some free credits to test it. And there are a lot of tutorials available on the website. So just create a new account, join, and you can download it easily. Okay, so let's try to simulate something with OnScale, and I'll show you how to actually do it. So the first thing you see when you open the OnScale software is that there are three modes: designer, analyst, and post-processing. So designer is basically the mode that we'll use to create our geometry and to do the analysis. So it's the graphical based mode, which is quite easy to use, so as you will see. Analyst mode is more code based mode. So if you are if you know PZ flags and you know the syntax of how to write the language, well, probably it's almost the same, so you can use the analyst mode directly. And post-processing is to see the results. So let's go into the designer mode and let's create a new project. Right, so let's call it 2D wave. Okay, let's go 2D wave 3 in my case. You have three types of models: 2D model, 3D model, or 2D axisymmetric. Here I'll start simple with a 2D model. Let's save that on your computer, so I'll just create a new folder here. Let's call it 2D. Okay, 2D wave 3. Okay, save that. Choose wisely the units and function of what you want to have, and then you are into the designer interface. So for the moment, the type of modeling options are quite limited. So you can do simple models using the 2D primitives here. So that I'll do. I'll use those and show you how it works. If you want to design a more advanced model in 3D, etc., you can also import your model in step format, for example. So this can be done using the import geometry, and you have different type of format and conversion available. So now let's build our first model. So when you create a rectangle, you have your first shape appearing, and the way to change the dimension is to go here in the property window and to change those properties here. So you have X, beginning, end. So if I change, for example, this to 0.06, you see that my model updates automatically, which is great. 0.03 here, and now I'm getting the shape I want. So if you have some problems to reset the view, you can go in model graphics and click on reset view here. Okay, so now I have one very simple shape. By the way, if you want to display the mesh on this shape, you can go also in model graphic, and there's an option called show meshing. So you can activate it if you want, or if you feel like it's a bit cumbersome, well, you can unactivate it for the moment. And now what I want to do is to assign pressure here. So my model is a steel plate I'll make a hole in the middle, and I want to assign a pressure here that will vibrate along to a certain time function. So time function called forcing function here. So I'll assign this load to a time function with a certain time distribution, and I'll observe how the wave is actually propagating into the steel material. So what should I do? So I have my first primitive. Let's create a material first. And you see that you have a material database inside the software, which is great. A lot of materials. So we go to milled steel generic, and I'll just add it. And then you have to assign it to your primitive. So right click, assign steel, and then you see that when it changes colors, it means it's okay. It's assigned. Now, how do I make a hole in this primitive? Well, basically what you have to do is to create a second primitive like that. So I'll have to set the right dimension for it. So the right dimension, so let me think about it. So I think for Y it will be, for X it will be 0.04 and 0.03. Okay, so now I have a very huge line, and for X, not for Y, sorry, this should be 0.04 maybe, no, sorry, 2, yeah, and 0.01. So it's very small, so let's reset the view. Okay, and now I have a second rectangle here, which is a primitive number 2. So maybe if you use all the kind of software before, you will think about how do you cut this hole into the first primitive and you generate your shape here. Well, here it's a bit simpler than that. Actually, what you have to do is simply to take this primitive here and to assign the material void, and when you do that, this actually this will actually remove this from your first model. Now what I found is that when you do this, the material here is unassigned, so I don't know why, so you have to reassign it. No, sorry, not this one. This one is void. The first one should be steel. Okay, so let's check. This is void, this is steel. And if I show the meshing, so now you see the meshing should be around this hole, and it will not consider the part inside the hole. Okay, so now that I have that, basically I'll have to define what is called keypoints. So keypoints is a way for the software to refine the grid around certain edges in which you want more precision. So you can just add a keypoint here. So the first time you do this, the axis, the view changes to this view here. So I don't know why. So what you have to do is to go into model graphics and rotate the model again like that. So it's probably some kind of small problem with the camera. I don't know why. And when you get that, you have to choose this edge here. Click on place point. Then you choose this one. Make sure you have 0.04, which is the axis here, and then kind of rotate in this direction and do the same for the other edges here. So okay, 0.01, and here it should be 0.02. Okay, so once you do that, reset the view. Okay, I can just hide that. And let's reset the view. Yep. So I have defined the key points. So now I just have to define my boundary conditions. So in this case, there will be only a loading, a pressure load, and on the other edges, I don't need to apply any boundary condition because there is no wall. It's just a wave propagating without any kind of reflection from the edges. So just go in the load, and here to select this edge. So if you have a step model, generally you will be able to select directly the edge, which is quite convenient. But if you are using primitives, you'll have to go into geometry interface, choose the primitive, and then choose the edge through this menu here. So side here, in this case, it's side 1x minimum, and create your load. Now this load here is a static load, so I need to assign a time function to it. So let's go to forcing function, time function, and you have also some kind of database of different kind of wave that you can give to your input. So let's use maybe this one, Blackman-Harris wavelet, and with a drive frequency of 1 power 10 secs. And also there's something that you should do, is that click on project settings, and there is here a frequency of interest. So it's optional, but activating that will help the solver to define the smallest size of for the meshing and for the computation. So because the OnScale uses an explicit algorithm, so it has to calculate the time very accurately in order to make sure that it solves your model as fast as possible. So it's better to give him this frequency of interest into the project settings. Okay, once you have that, go into okay, so constraints in this case we don't need. Make sure the domain boundary are all set to 3, like that. But there are other options if this is what you want to simulate. You can absorb and fix impedance, etc. But I'm not presenting that today. And once you do that, now you can set up your analysis. So for example, let's set it up as dynamic. So it's a time analysis, so it will calculate everything according to time. You can choose single precision, double precision, maybe to have better accuracy. Now this is important, the simulation runtime, how long do you want it to be? So it's very, very short time analysis because it's a sound wave propagating, so sound waves propagate very, very fast. So for this simulation, the runtime is 0.0005. Now that you have that, the only remaining part is to define the kind of output you want to get. So by default you'll get the velocity, but it's better to add different kind of outputs. So we can add, for example, time history at a certain position. So time history can be time history of acoustic pressure, displacement, velocity, stress, or any kind of output results. So let's choose acoustic pressure, and let's define a position inside S model. So here we just give it the position. So X will be 0.03 and Y will be 0.015. Okay, and now I'll be measuring the acoustic pressure time history just at this point here. So I could choose other points if I want. And let's add another type, which is, for example, field data, which will help me to measure the maximum acoustic pressure in all the model. And once you have selected the kind of outputs you want to get, select the runtime graphics. So the runtime graphics is the small window that opens as soon as I will launch the analysis. So you will see that. You can like that add, let's say, 2 views, which will be vertical split. In the first view, let's display my time history. Okay, my time history, or maybe let's play, yeah, time history of my output 1 at this point. And for the second view, let's display an array of acoustic pressure, maybe maximum. So if I set maximum, I will only see the maximum, so it will not change. And you can select the number of frames you want for this. So if you want the animation at the end, then you will have to record array of you will have to record a snapshot. So maximum, so let me check. Okay, yeah, the snapshot is in the outputs here. So I need to add an additional output 3, which will be data snapshot. So I'll be able to output all data along time of the acoustic pressure. So that will allow me to get the animation after that. Save your projects, and if you didn't do any mistake, you can run the software. So if you're using the free version with your free credits, you can use the run on cloud to run on Amazon your analysis. So it allows to run very, very huge models very quickly, and it's scalable. So in function of your analysis and your needs, you can use that. Or if you have the private cloud function, you can use run local. Okay, so here it tells me that I didn't assign my time function, so I forgot to assign the time function to my load. So you need to go to load, and in the properties there is driving function, so you need to assign the driving function here. Okay, and now it seems to be running, and I'm getting dynamically my results. And here this is maximum acoustic pressure, so it's kind of fixed, and now it's computed, it's finished. So I can go to the post-processing. So to go post-processing, you have to click on the very small buttons here on the right top corner called post-process, and go into data out or flex history maybe, and you can open flex history file, and here you get the acoustic pressure. APRS means acoustic pressure. So now I'm getting the value of acoustic pressure at the point I selected previously, and this is my time function that actually I defined for my own input. Now let's see the snapshot and the other type of results. So I have to open it like that. Yep. So my snapshot will provide me for every time step. Okay, view slot is already occupied. Okay, so I need to open, I think I can open a new view slot like this to view my acoustic pressure. So, and if I want to see the animation, just right click, plot data over time, and then you will have the 20 frame that you selected previously to run that. So if I just run it, I'll be able to see the propagation of the wave. So it's difficult to see what we are actually seeing here. We are looking at the acoustic pressure. So acoustic pressure is the difference in the pressure from the environment pressure, which is created by the propagation of the wave. And to represent what it to see the wave, actually you have this surface plot which will allow you to view it like that, let's say in a more graphical manner. So you can imagine the wave going in this way, and then in the next time step, well, it looks different. So here I have 20 time step. If I wanted to get a better view, maybe I should set up much more than that to have a more granular type of view. And yes, and that's it. So you are able to view the animation, to view different type of results, and to get your time history. Now, if you want to come back and run again the analysis, there's a small trick to know, is that you have first to clear the workspace. So the software will close all those data files, and then you can go back to pre-process, change some options, change some kind of variables or anything you want to change, and you can run again the analysis. If you don't close the results, then it will tell you that it cannot write on the result file. That's because the file is not closed. So anyway, this I think this is the end of today's tutorial, and I hope you will enjoy also trying OnScale with different types of wave and different type of materials, and to see how it propagates. So thank you for watching, and see you next time. If you're interested to know all the other kind of models you can simulate with OnScale, you can visit this page, onscale.com/applications, and you'll see everything you can do in MEMS and filters, sensors, sonar or medical type of applications. And they have also very good tutorials and models that you can directly download to try.